No, no, it's downhill. It's all downhill, actually. And I'm not saying like it's like average grade downhill. It's all literally downhill.
Oh, so the walk back.
Yes, the walk back would therefore be 100% uphill. If I make up. Yes.
We're finishing that.
We're gonna finish class out there. Yeah. Finish class out. We're gonna finish out there, yes, ma'am. So, did anybody catch a small statement I made when I said calculate the grade of that tilt? I said, use 6 or 8 or use 3 or 4. It doesn't matter. Did you catch that little throw out? I said, it doesn't matter if you do 6 and 8, 3 and 4. Some of you weren't even. So you weren't paying attention. It came out to be the same exact thing. Now, the way I've drawn that isn't quite correct. The way I've drawn that isn't correct because you can't be 3 and 6 at the same time. If I were to draw it correctly using the corresponding colors, it would look something like this. Let's see, that would be the 8, right? So we'll make it. I'll try to draw it to scale. A little bit shorter. That's probably pretty close. Pretend it's a straight line too, if you would. There, it's pretty close. I'll put a right angle in there to make us happy, even though I don't have to with those numbers. Oh, FYI, this kind of triangle is often used by carpenters when they want to square up a room. For example, if you put a length of wood 6 feet long, 8 feet long, and 10 feet long together, it forces a right angle between the 6 and 8. So I drew that right angle in, but it's kind of unnecessary. It's automatically there. So when you're checking the square on a room, if they want to make sure it's square, they'll oftentimes use these, they're called Pythagorean triples, to do just that. They'll take a diagonal measurement and say, this diagonal measurement should be this if the room is plumb. And if it's not, then they move the walls around and they square it up so that it is plumb. So which is pretty badass, actually, if you think about it. Very basic geometry being used to make very big spaces. Okay, so that's the green one. Where would the blue one be if I nestled it in there? Where would it be? Where would it be? If I wanted to overlay it on top of that green one. Christy, go ahead.
I believe that the rise would be halfway down the 6 side, and then the run would be halfway down the 8 side if you put it up against the 90-degree angle.
Can I put it right here instead? Is this what you mean?
Oh, no.
Can I put it like that? Is that okay? Is that all right?
That would be quite
Is that fair-ish? Okay. So I like the halfway. Where'd the halfway come from?
Well, 4 from 8 and 3 from 6.
So I could have tucked it in as well here. I could have tucked, I think that's what you were talking about, but I think if I do it this way, I kind of get kind of a neat, fun point across to you that way. So if we do this, now we know that this guy here is 3. I've made it be 3. This guy here is going to be 4. I'll draw this line here so you know it's just that and not the whole green thing, and I'll make the green thing be. That's red. That's black. That's green. And then the 10 is this guy here, but the little dude here is 5. That little guy there is 5. Have you guys ever used a copy machine to make an enlargement or shrink a document? You are using this idea. This would be a 50% shrink on the green triangle, or a 100%, or 200%, I guess, a 200% increase on the blue one. If you're going blue to green, you'd have to put it on the copy machine and increase it 200%. Or increase it 100%, but blow it up to 200% of what it is. If you put the green one on the copy machine to get it to be the blue one, you have to shrink it by 50%. So those shrinks and those increases are called scale factors. And the reason they work is because these triangles are said to be similar. This is one of my favorite ideas, similar triangles. This is one of my favorite ideas in geometry, similar triangles. I used to teach geometry in high school for years. And there was a lot of emphasis placed on what are called congruent triangles. And I realized very early on that congruent triangles are ridiculous. We'll talk more about those later on. They're ridiculous for application in the world. Similar triangles are much more concise and much more applicable and useful. So, what are similar triangles? Well, here's the definition. This is a simple definition. 2, and I can put or more, because you can have more than 2, but in this class they'll just be 2 at a time. It gets a little crazy when you start having more than 2. So 2 triangles are similar And this is just a definition, okay? There's nothing, this is something human beings made up because it has a bunch of fun properties and it has a bunch of applications everywhere from, like I said, solar eyebrows to measuring the height of mountains to mapping India. You know, all these are similar triangle ideas. Two triangles are similar if, and let's do it a little 1, 2. There are two things that happen. Number one, if all of the angles in one are equal to the angles in the other. That's the first thing. That's the first thing. And this is, Christy, this is why I laid the triangles like I did. I wanted to lay it like I did because I wanted to drive home the point of the angles being equal. And you get a freebie by doing it this way. Not that your way isn't badass, because it totally is. And you actually get parallel lines with your way, which is really cool. But this way, we actually get the congruent angles. So this means in the blue triangle and the green triangle, the angles are all the same. If there's a 30-degree angle in one, there's going to be a 30-degree angle in the other. If there's a 60-degree angle in one, there's going to be a 60-degree angle in the other. Can you see where the equal angles are between these two triangles right now? We're going to blow them apart here momentarily too. We'll blow them apart as well. But can you see where the equal angles are in the blue and the green? Can you name one of them? Name one of them for me.
45?
There might be actually there won't be a 45 in these. There could be a 45 in general. What's the one that's marked?
90.
There's a 90 in each of them, right? That's what you meant. I kind of figured, actually. So I'm going to put little dots next to the ones that are equal, if that's okay with you guys. That's equal to that. It's kind of like a little face looking at you. Where are some other ones that are equal? Josh?
Well, you see how you have it, the blue one kind of to the left and it all lines up? That one angle that's kind of lined up, that's one.
That is actually, believe it or not, two angles, isn't it?
Oh, yeah.
It's in the blue triangle, and it's also in the green one. So what I'll do is, I'm going to draw, here, I'll draw very small versions of the triangles up above, broken apart, so you can see that, if that's fair with you guys. So we'll do a little blue one here. And then I'll try to make this green one look twice as big. Let's see how good a job I do. Nail-ish. So the right angles, definitely. This guy right here that I put two dots in, he exists here, but he also exists there. Doesn't he? He also exists there. Pretty cool. Now, how about the third angles? Are they equal? Convince me why they have to be equal. Because we can't use Josh's cool idea, can we? We can't use Josh's cool idea because they're not laying inside of each other. So convince me that the third angles have to be equal too. Tell me your name again.
Ashley.
Ashley, please go.
Because they have to equal, a triangle has to equal 180 degrees, and since you have 90 degrees, there's two left, and you divide it that way.
Ooh, let's follow that logic. You hear what Ashley said? I loved it. So we know from back in the day geometry, the three angles of a triangle have to add up to 180 degrees. So this plus that has to be 180. And that plus that has to be 180. Well, if those two are the same, and those two are the same, is there any way these could be different? They can't be different. If they were different, then at least one of them wouldn't add up to 180. So they're forced to be the same. Boop. Here it is. So there you go. As a matter of fact, the postulate that's often quoted in geometry class says if two angles of one triangle are equal to two angles of a second, then the triangles are similar. They don't bother saying all three, because you don't have to say all three, right? You don't have to say all three. If you've got two, you've got the third one automatically. Does that kind of make sense? It's called degrees of freedom in statistics. We'll talk about that when we get to 243, some of you guys. It's a fun little idea. Once you've gotten rid of all but one, the last one is spoken for. So, cool. That's the first thing that's true. So have you ever thought about that? Chances are you don't. But imagine taking a document and putting it on a copy machine. You put the document down, you increase it to 200%. Well, actually, you probably decrease it more often than increase, don't you? I bet you shrink it more than you. So let's say you decrease it by 50. So you put the document, a piece of paper, rectangular piece of paper, on the copy machine, shrink to 50, go, shoot. Do the angles shrink by half? That would be kind of silly, wouldn't it? Because then you get this little diamond out. All the 90s would shrink down to 45. The angles are maintained, aren't they?
Yeah.
The angles stay 90 degrees. So what changes by 50%?
Side.
Be brave, be brave!
The hypotenuse.
The hypotenuses or the legs or any of the sides, right? And that is the other part of similarity, and that's the part that makes it super useful. That's the part that makes it super useful, is part the second. I'm going to write it, and I'm not going to write it down here. I'm going to write it over there if it's okay with you guys, because we're getting kind of low to the ground. I want to make sure you guys in the back can see it. We might not make it outside today. Is that okay? That's great. So we will make it outside on maybe Monday, and that way you can park more effectively, maybe. How about we do it that way?